Hello everyone from Jagiellonian University, Krakow, Poland. Today we are thrilled to announce that we have Balázs Patkós from Hungary, Budapest, Alfréd Rényi Institute of Mathematics. He will be talking about an interesting topic, finding the diameter of a tree with distance queries. He is an editorial board member of everybody's favorite discrete math journal. Thank you for coming, and the floor is yours.
Thank you very much for the introduction, and thank you for the invitation, and thanks everyone who was involved in arranging my stay here. This is my first time in Krakow. I enjoyed it very much. Even the Hungarian Prime Minister came along. We managed to avoid each other, but still he was here yesterday. Okay. So, first of all, this is joint work with Gerbner from Rényi Institute and three PhD students from Eötvös University, András, Imolay, Kartal, Nagy, and Kristóf, Zólomy. So my main research area is about set systems, so I asked Nika whether it is okay to give a talk about those kind of things, and he said whatever I choose, but just to be informed, this is a theoretical computer science seminar, so I opted for something different. There is a very narrow thing that overlap between my research area and something that can be called computer science, and that is combinatorial search theory. We have a seminar in the Rényi Institute with this title. That's a research seminar. And so the history is this, that Alfréd Rényi, he was a probability theorist, but had not too many, a couple of papers on something that he never called combinatorial search theory, but something that now we would call that. And then his former student, Gyula Katona, who is my former supervisor and who is a former director of Rényi, he has many more papers on combinatorial search theory, yet it's not his favorite topic, or not most research topic, but probably because of, in honor of Rényi, he keeps continuing. And now people who are attending this seminar, they have kind of the same thing. They like this area, but it's not the main research area for any of the participants. So this is promising for today's talk, because that means that you won't see any very heavy machinery. So if you don't understand something, then it's my fault, because there won't be any kind of very deep or hard ideas. So, okay. So what is this? Okay, good. So, if you are searching for learning a hidden subgraph or something like that, you will find many papers. So there the idea is this, that we have n vertices, labeled vertices, and there is a hidden unknown graph on these vertices, and we want to know something about them, a property, whether it is connected or not, some parameter, or we want to know what the graph is, what is its isomorphic class, or the labeled graph itself, what we want to determine. And we can ask questions, and of course we want to ask the minimum possible number of questions. So usual queries, so-called, we can ask whether a pair is an edge or not, or in more general, we can ask a subset of the vertices and ask whether they form an independent set in the unknown hidden subgraph, or there is an edge within that subset. So this is the general way, but today it's a little bit different. So first of all, we know that the hidden subgraph is a tree, and what we can only, so our queries are of the form of a pair of two labeled vertices, but luckily we will get a little bit more information than, well, if it's an edge, then we get the answer that it's an edge. But if it's not an edge, then we get more information because we get the distance of the two vertices in the tree that is hidden. And what do we want to find out? Well, as the title indicated, the diameter and or two vertices of maximal distance. Another option is to determine T up to isomorphism or determine T completely, so the labeled version that was hidden, and we will be talking about adaptive and non-adaptive strategies. So adaptive means that we ask the first question, we get the answer, and based on the answer, we can decide what is the next query going to be, and so on. As opposed in the non-adaptive case, we have to ask all queries at once, we get the answers, and after getting the answer, we should be able to determine whatever our job was. And the way how we think about this is kind of like a two-player game. There is the questioner and the adversary, and I always make this joke to whenever I lecture about similar things to my US students at Budapest University, that in Hungarian it's much better, because there the adversary is called the evil dwarf, the gonosz manó, and so, but actually, so anyhow, in English it's just adversary. So what they are doing is that they are playing the game that the questioner, sorry, the adversary was thinking about the, or he hits the tree, the questioner is trying to find out what the tree was, or what is its isomorphism class, or what is the diameter. So asking questions, and the adversary's goal is to delay the end of the game as long as possible, and the questioner tries to figure out the answer, the final answer, as soon as possible. And if they are playing according to an optimal strategy, then of course this is what we are interested in. So that's the minimum number of queries that we are looking for. So for lower bound, we will always give an adversary strategy, and for an upper bound, we are always going to give a questioner strategy. Okay, and here are all the results. So from here on, you can go back to, yeah, okay, let me not finish this sentence. Anyhow, so the reason for this being red is that all the others are our result. This is the starting point.
Games, it's not like
these are. I don't think it's an online game because.
Well, okay, sure, it's a game, but how would you argue that there is no value in this case? Like the best strategy, the best what can questioner force, adversary force, is what questioner can hold.
Yeah.
It's simply define.
Yeah, I think so. Yes.
Okay, I will just execute.
Okay. So the results are that in the adaptive setting, if we are looking for the diameter or two vertices at largest distance, then it's 2n minus a constant, somewhere between 2n minus 4 and 2n minus 9. As I said, this 2n minus 4 algorithm is the only result on the board that is not ours. And then adaptively determining the tree up to isomorphism. This is the only case where we don't know the asymptotics. We know that it's between n squared over 8 and n squared over 4, up to some error term. If we want to get the exact labeled copy of the tree, then we need roughly n squared over 4 queries, the worst case. And actually, we also showed, this is just an additional result, that we have a not very complicated tree, that even if we are given that this is the tree, this is, the hidden tree is isomorphic to this one, but now we are interested in the exact copy that also requires quadratic, actually, n squared over 8 queries. In the non-adaptive case, the thing is a little bit more boring, because you almost always so you have to ask in all questions almost all pairs. So n times n minus 3 over 2 to find the diameter or determine the isomorphism class. And if you want the labeled thing, then you have to ask almost everything. So n times n minus 2 over 2 instead of n choose 2, which would be the worst case. Okay, and so my plan is to give you some hints about all the proofs. So let's start with the one that is not ours. So on math overflow, Raphael Coxon, a French researcher, showed this algorithm for the questionnaire, how to determine adaptively the maximum distance, choose a vertex V, this guy over here, and ask all distances to all other vertices. And that will give you the layers. So those that are answered 1, they are the neighbors, then the second layer, and so on. And you just don't know what's in between, how they are connected. And then what you do in the next round is that you take someone that is furthest away from V, so here this is this U, and ask all the other guys again. Of course, you don't have to ask the query UV once more. And also, you don't have to ask one of the neighbors of it. So you figured out who are the neighbors of V, and you don't have to ask all of them. And you can argue that actually if V had only one neighbor, that's even better. But in that case, but otherwise it's even that you ask 2n-4 queries. And so just a remark or 2 remarks. So why don't you need to ask all of them? Because of course, so I don't know if U is at distance 7 from V, then all the neighbors are at distance 8, with the exception of one that are at distance 6 from it. So if you know one but all of them, then of course you can figure out how
How do you know which one?
So that's what I'm saying. If you are asking U with all the others, and you are asking all these but one, so suppose that U and V had 7, then if you know that, okay, all the others were answered by 8, then this is its predecessor, so that there the distance should be 6. If 6 was already taken, then all the others are actually 8. So that was one thing. And the other thing is that I won't be talking about this today, but so there is, sometimes people are considering models between adaptive and non-adaptive. So adaptive means that you can always decide the next query based on the previous answers. Non-adaptive means that you have to ask all of them in advance. And there are things in between when you say that you have R rounds. So there are R time slots when you are at the first moment, you ask some number of questions, some number of queries. When you get the answers, then based on those, you ask the second round of queries and so on. And there might be a fixed number of rounds that, I don't know, you have to ask all the, your questions in 7 rounds. And then that's something in between an adaptive and a non-adaptive strategies. And what you see here, that this is a 2-round strategy, because we can ask, you can pick our favorite vertex V, ask all the distances to be in the first round, and then based on those, we pick our vertex U and ask all the other queries. And that's so so this optimal thing is it works in 2 rounds. So somehow, and as we saw, that the non-adaptive case is much harder. That's there the answer is quadratic. So, but already if you allow 2 rounds, then it goes down to linear. And I don't want, so all what you need to show that I mean, this strategy is correct. So the maximum distance is taken maybe at some other places as well, but at least one of the largest distances U and something else. So whenever you find 2 vertices, then you can replace one of them and make a larger with U. But so that's an exercise. It's not very hard to show it. Okay.
So we have to limit the number of rounds.
Sorry?
We have to limit the number of rounds.
So
so if I just ask one question and then based on that, add another question and then keep going like that, because here it's 2 rounds, right? And the list of that question 1 round, and then based on that list of thing, and do the second round. Either 2 process different or the same. You get what I mean?
So
you do 2 rounds here.
yes.
First round had a list of questions.
I get all the answers.
And then
based on all these answers, I take the next set of questions, and after the second set of questions, I'm capable of telling the answer. So this is a 2-round algorithm. And what was...
As the second way is I ask one question, and then based on that one, ask the next question, and based on that 2 things, keep going like that.
Yeah, and that's what we call adaptive, and there is no bound on that. So, and non-adaptive means a one-round algorithm, 2 round, 3 round, whatever it means. What it means that you have 3 places or 3 times when you can ask your queries. And adaptive means that it's up to you. So basically, it's not worth, I don't know, asking several queries together, because why not have the extra to get the answer? Okay, so the lower bound, well, the hint is on the picture. So so now we want to give an adversary strategy, and so the adversary has to think about it. Okay, I need to answer in such a way that for a long time my answer should be confusing enough that no one could tell what is the largest distance. So most likely, the adversary has to think about one type of a tree which is confusable with another type of a tree. And so here are the 2 types. So the double star on the left, and this is something that we call in our manuscript a real caterpillar. So double star, I think that's fairly understandable. So here the diameter is 3. On the other end, what I do here in the picture is that I move these 2 blue vertices to the other side. Then the diameter is 4. And even worse, there are no pairs of vertices that are at the longest distance in both of the graphs. So here, a blue and the red vertex here are at, and they are only at distance 2 here, so they are not. So the strategy will be that, okay, try to answer in such a way that these 2 things should be consistent with my answers as long as possible. So let me formulate it in an ugly lemma or a longish lemma. At least it's a little bit more than 5 lines. So what it says that, okay, I mean, and this is exactly what I want to do, that I want to be able to move these 2 blue vertices to the other side. If I'm able to do that, then there is still possibility to confuse the 2 things. So a partial distance graph is just that a graph on the same set of vertices, and an edge might be is labeled by an integer number, which should be the distance of the 2 end vertices in the original graph. So if I have a partial distance graph of this double star, and if there is an edge between this red guy and this blue guy, then that should be labeled 2, because that's their distance. So it need not have all the edges, but whenever it's there, then it should give us the distance. And so the question is that if I have a double star, then what kind of a property of a partial distance graph is what it makes G such that it's also a partial distance graph of a real caterpillar like this. And so here it is. So if I'm looking at the components on induced on the left side, and I find so suppose that these 3 red vertices, they form one component, and these 2 blue vertices, they form another component, and there is a red vertex on the other side, such that this red vertex is not connected to any of these 2 blue vertices, then I can move it to the other side. This is what's written over there. And why is that so? Because then, well, I don't have to, but because they form separate components, so I didn't ask any queries between these red guys and these blue guys, so I don't know anything about their distance, so there is no confusion with them. And I didn't ask any query with this red guy and any of these 2 blue, but in both of the graphs, the distance of a blue guy and the black guy is 3. If I'm not no, it's it's 3 for these guys and 2 for this one, so that remains the same. So there is no problem with that. So if my partial distance graph satisfies this property, then my job is not yet done. At least one more query is needed. So now the adversary knows that as long as is possible to maintain this property, the play is not yet over. Okay, so now here's an even longer lemma. The lucky thing is that the first part, so until the furthermore, the red word, it's just the negation of the previous one. So now it just says that, okay, it's over. that means that so I mean, I don't have the property before, so every vertex on the right is connected to every component on the left and vice versa. So there is no I'm not able to play this game of moving one component to the other side and tricking the questioner with this. And then, if I also have that with in the partial distance graph, or that part that is going between the two sides, there's a subgraph F that contains at least n-1 vertices, so obviously it's going to be a spanning tree, and it has a vertex in the smaller side that has at most degree 1 in this subgraph. Then actually the total number of edges, which will correspond, of course, to queries, is at least 2n-7. So this is the lemma, and, well, okay, it's so easy that why not prove it. So C sub x and C sub y denote the number of components in the two sides. And if the number of components in the smaller side is at least 5, then it's very easy because, I mean, the assumption is that every vertex on the right side is connected to all the components on the left side except the one that contains the center of the double star. So it has at least 5 components. So it is every vertex is connected to at least 4 components. So that there are at least 4 times the number of vertices in Y minus the center that many edges. And because Y is the larger one, so it's at least 2n-4. Okay. So what happens if the number of components in the smaller side is small, so at most 4, then within the left side, I have at least size of x minus 4 edges, because the number of components is at most 4. On the right-hand side, well, I don't know how many components are there, but definitely there are at least that many edges. And in between, I have this strange subgraph F that contains at least n-1 edges. And also I have this X prime who has 2 properties. First, that it has only one adjacent edge in F, and also it is connected to all the components on the right-hand side. So that means CY components. Well, I cheated because it's, I mean, one component was, the component of the center was not necessarily, so it is connected to CY minus 1. One of them can be the edge that is in F, so all the others are new, and if you add it up, then you get 2n-7. So it's a relatively simple lemma, and so based on that, the strategy is now for the adversary is simple. The question is, what can it be carried out? That he wants to answer in such a way that F should be there. So somehow his strategy should be such that during the game that F should be born. And so how is that? So he can give away some, the adversary can give away some extra information that whatever is going to be the first query, he will answer 1. And he also tells that that's going to be the 2 centers of the double star. And he tries to answer in such a way that as long as possible, a real caterpillar is also consistent with his answers. So based on that, basically every answer or every every answer to any query is equivalent to saying that whether it's on the same side, whether the 2 vertices are on the same side of the double star or not, or they are on the opposite side. Because if you are asking a center vertex and something else, then it's either 1 or 2 that's going to be the answer. If it's 1, that means that they are on different side. If it's 2, then they are on the or sorry, I mean in this way it's other way around. So 1 means that they are on the same side, and because it belongs to its star, and if it's 2, then it belongs to the other center star. And the same for if you are asking 2 non-center vertices, then it's either 2 or 3, and again, it just means that whether they are on the same side, whether they are connected to the same center vertex or different center vertex. And the strategy is, because we want to build this F, which lives hopefully in the graph that connects the two sides, we are trying to force as many edges as possible. So if it is possible, then we are answering opposite side. So let me just show. So here's the start of the game. We always answered opposite, that means red, and this time we are forced to answer same side because the red graph is a bipartite graph, so if they are already on the same side, then we can't cheat. So okay. So let me go back, and so we maintain two graphs. G1 is the graph of those queries that were answered opposite, so the bipartite graph, and G2 is the disjoint union of the two sides, or whatever was within those. And okay, so there is one more technical lemma, and so this will be so it says that if we have a bipartite graph with three connected components, so this is when the G1 graph, the graph of the queries that were answered opposite, they have three components. Then we can add two edges to this graph so that now it becomes out of the three components, now it is connected. And it will contain a spanning tree that we believe that's on the smaller side. So it will exactly satisfy the condition of the previous lemma that I said. So this is the lemma that I won't show you the proof of. It's a case analysis, not very complicated, but I don't know, we have 4 or 5, I don't know how many cases. So based on that, that means that there will be a special moment. So I mean, the game is played. The adversary answers according to the strategy that he always tries to answer opposite side unless he's forced to say same side. And the first moment when in the opposite side graph there are only three components, then based on this lemma, he gives away. I mean, he finds those two edges and gives away the information without asking that these two edges are actually members of my graph. So F, our future F in the end, will be there. And then, of course, these two edges will not correspond to queries. They are just fake edges or fake information or extra information. And, okay, so here it is again. So let me show you. So this is a possible, it's a possible moment, and it shows that at this moment the graph or the game is not yet over, because on the left side you see these three blue vertices. They form a component. A component that doesn't contain the center U, and on the right side, this red vertex is not connected to any of them. So both this double star and this real crater pillar is still possible. So the game is not yet ended here. So what we need to prove, what I want, is that actually the game cannot be over before that special moment. So before, if the graph of oppositely answered queries have more than three components, then the answer can't be determined. I mean, the diameter cannot be determined. And if that happens, then of course we know that at the end of the game, in our query graph, there will be 2n minus 7, or this in G1 union G2, there will be 2n minus 7 edges. 2 of them might be fake because of that special moment, but all the other 2n minus 9, that those correspond to queries. And this is the proof. Any questions concerning this one? Okay. So the next statement was that if I want to determine completely the hidden tree, then I need n squared over 4 queries. And so actually the adversary tells the extra information that the tree that he was thinking about has radius 2. So there is a center, there are its neighbors, the inner vertices, and there are the other outer vertices, and there are exactly, so n half inner and n half outer vertices, or n minus 1/2 and n minus 1/2 inner and outer vertices, and even this partition is known, is given away. And so then what are the meaningful queries? Of course, I mean, if we believe, and we do because we don't lie, so in that we believe in this information, then of course there is no point asking the center vertex and the inner vertex, because the answer is going to be 1. There is no point asking 2 inner vertices, because the answer is going to be 2. So it's either 2 outer vertices or 1 inner and 1 outer vertex. That is a meaningful query. And again, our strategy is that, okay, always answer the larger one. So if so it's for an inner and an outer vertex, it's either 1 or 3. As long as we can, answer 3. If it's 2 outer vertices, then it's either 2 or 4. Answer 4 as long as we can. But if I do that, and I promise that, or if I do according to this scenario, that means that there is no point for the questioner to ask a query for which 1 was the answer or for which 2 was the answer, because that would have been 4. So he should have known this information before. Now, suppose the questioner arrived to a moment when he's able to figure out the whole tree. It looks like this. But because of what I said, that there was no point of asking a question where the answer was 1 or 2, that means that in here, there was no query. And within here, there was no query again. So that means I will try to count the queries in such a way that, okay, for every pair I, j, so I and j, they are for the inner vertices, so this is v sub I, the ith inner vertex, this is v sub j, the jth inner vertex, and whatever they are connected to. And so the question is that how many queries are completely within this graph? And the lucky thing that based on my strategy of answering, there is no query that is completely here, and there is no query completely here, because this is what I avoided, that I always try to answer 4 or 3. So if it's a forced 1 or 2, then why was it asked at all? Now that means that I don't overcount anything. So I mean, then every query goes somewhere between here and between there. And so everything is counted only once. And I claim, which is written over here, that this graph, so the queries between these 2 parts, the inner vertices included, it cannot have more than 2 components, because if they do, then there is one component that doesn't contain neither v sub I nor v sub j. And then I can flip that component. So whatever in that, so suppose that, I don't know, this vertex and this vertex, they form a component, then I can just flip that this one now is connected to Vj and this one connected to Vi, and everything is still possible. And because now I'm interested in determining the tree completely, then there is confusion. So that's impossible. So if there are only 2 components, then the number of queries is at least the number of the outer vertices in these 2, because I mean the 2 other guys so it could be the number of vertices in total -2, but that -2 that goes for the 2 inner vertices, and if you double count this, then you get n squared over 4. Okay, so this is the lower bound, and of course it was a bit of cheating. I should have started with the upper bound, because that shows that why we had to choose, or why was it meaningful or to pick this particular, so this radius to 3. So the upper bound is very easy, and again, it's a 2-round algorithm. Again, pick a vertex V, and ask all distances from this particular vertex, then you get, so these are its neighbors, second neighbors, third neighbors, and so on. And then we know that because we are talking about a tree, all the edges go between consecutive layers. So it's enough to ask all those. And they form a bipartite graph, so at most n squared over 4 edges, you will always get all of them. And then, of course, you know that if there are more than 2 layers out later that, then it's going to be just inverse. So that's why radius, we were looking for radius to trees to get the lower bound. Okay. So I promise something like this, that there is one particular tree, I call it a spider. It's a special spider, so all the legs have length 2. Well, if n is even, then of course there is one exception with length 1. And so even if we are told that this is the tree, I mean the isomorphism class, then n squared over 8 queries are needed. Because again, we can do very similar strategy. We give away the information that who is the center, which are the inner vertices, which are the outer vertices. And the strategy is again, in that case, of course, because we know that this is it, so that means there is no point. So the only informative query is an outer vertex and an inner vertex. All the others are known. So if there are 2 inner vertices, that's 2. 2 outer vertices, that's 4. So the only meaningful query is 1 inner vertex and 1 outer vertex. And what we want to do is always answer 3. And again, so we would only answer 1 if forced, but then what is it good for? And then all what we need to see is that for any I and j, one of the cross queries had to be asked, because if not, so neither this nor that, then we could change that. Or maybe I point it like this, that if neither Vj with Wi and Vi with Wj were asked, then of course I could flip the neighbors. And then we don't know the exact label tree. So we have, so for every pair out of the n½ legs, we have to ask 1 query, and that's again n squared over 8. And okay, so it's not very hard to come up with an algorithm for the questionnaire. That first, in a linear number of queries, so we can find the center of the spider, and then find the neighbors and the so the inner vertices and the outer vertices. So that's just a linear number of queries, so the error term. And then once we have the partition, then of course we just want the matching in between the inner and the outer vertices. That's what we need to find out. So we take our first outer vertex, we figure out what its neighbor is, asking all but one of the possible neighbors. They will always answer. I mean, once we get the yes answer, we are happy, so probably we will get it for the latest. But for the second outer vertex, we won't need to ask the neighbor of the first vertex, so it's one less, and so on. And if you add it up, that's what you get. Okay. And the last adaptive thing is when we want to have, so first of all, so this is the only question where we don't have the asymptotics of the answer. So the n squared over 4 upper bound comes from the fact that even if we have to find the labeled tree, that we can do with n squared over 4. So of course, if we are only interested in the isomorphism class, that can be only easier. And the lower bound is similar. Again, we think of a spider, but we don't give this information away. So this time, so we are going to answer everything as before. but we don't give the information away. So it might happen that a 1 or a 3 or a whatever answer will be coming, because that could help to prove that actually this was a spider. And again, what I want to claim is that there should be, so as long as possible, I will answer the larger thing. So I will, in my head, I know that who are the inner vertices. With the center, I will answer 1, but otherwise I would go for the longer. So if an inner and an outer vertex is asked, then I will go for the 3 instead of a 1. So the claim is again that somewhere in between, so either the 2 outer vertices, or Wi, Vj, or Vi, Wj must have been asked, and it's not very hard to see. So if, for example, this wasn't asked, then so if none of those were asked, then of course, sorry, how was that? So if one of them was, so if this wasn't asked, then you can, and neither this one or this one was asked, then it means that instead of this spider, you can connect this W sub I to Vj like this. So that means that now I have to show that what happens if both of them were asked. So both this edge and this edge was asked, and I get the answer 1. But then what happens? So why is it true that these crossing things must, or at least one of them must have been asked? Because I said that my strategy was that as long as I had the chance, I always wanted to answer the larger possible, so it's a 3 instead of a 1. So whichever of these 2 edges were asked first, I still had the possibility to say that, oh, it's not connected to this one but to the other one, so I should have answered 3. So if I answered both of these as 1, that means that, okay, there must have been a reason, there must have been something going in between, an extra query asked. So because of that, again, out of these n-half flags, at least for every pair, there was an extra query. So again, I have my n squared over 8 lower bound.
So Wi, Wj is by definition 4 if I is not equal to j. So the assumption here is that we don't know what the set W is? Or is figuring out the set W a pre-step?
So it's a lower bound. So that means that I'm giving an adversary strategy. And the adversary strategy is that I try to answer as a spider. So I have...
Oh, you're not guaranteeing it's a spider.
It's not. I'm not guaranteeing it, because this is what I mean. This time the task of the questionnaire is to determine the isomorphism found. So I will answer according to a spider, but in such a way that for as long as possible, I should be able to confuse this with something which is very similar. This one, which is just by one edge, it's not a spider. So I don't give away the information, but I answer accordingly, similarly.
So before you were assuming that there is no question about the pair of outer vertices. But here, these questions, they could actually help us distinguish these cases.
Yes, so they can. So that's what I'm saying, that out of so this time not out of the 2 crossing edges, but out of the 3 crossing edges, one of them was asked. This is my claim.
But even if Wi, Wj was asked, you still don't know whether they weren't flipped. So you need to ask 2 of those 3.
But it's isomorphism. So flipping means that it's still the spider, so that doesn't help me. So I don't gain any further thing, which is good because I have no, I don't have another. So it could help, but unfortunately it doesn't. So is it okay? By the way, the manuscript is on archive, so if you want to check the details, then you can do it. Okay, so now non-adaptive algorithms, and yeah, so the funny thing, so as you see, the answers to these two questions are the same, and it's not by chance. Or I mean, at first sight, it seems by chance, or it is, but then it turns out that actually whatever query set, because now we are talking about non-adaptive algorithms, so that means that I just have to tell in advance that which pairs I'm asking, so it's just a query set. So the same query sets are good for the first problem as for the second problem. So, yeah, okay. So the lower bound for the first question, that which is the diameter, and of course, if I want to know the isomorphism class, then of course I have to know the diameter too. So that means that the minimum degree of the query graph, so if I put an edge there, if I ask that pair, it should be at least n-3, because if there is a vertex v that wasn't asked with at least 3 other vertices, so say u1, u2, and u4, then the adversary will answer in such a way that this one and this one, I mean these two, so this is a center, and here's a path on 5 vertices, and this is almost the same except that v is not connected to u4 but to u2, and you can easily check that all the distances are the same except between v and u1, u2, and u4. So I mean, so v is a leaf, and it is here. It is connect. I mean, in both cases, it is connected to something which is just a degree. So okay, and then so that means that it's the only the distances according to v. So distances between pairs where v is involved, they can change. And v, the distance of v and the center vertex is still 2. The v and all the left-hand side vertices is still 3. And these pairs were not queried. So if there is a vertex v that was not queried with at least 3 other vertices, then it's impossible because and of course, and here the in the left-hand side, the diameter is 4, and here the diameter is 3. So I can't distinguish these two cases. Okay. The upper bound is harder, but as I said, it turns out that so if every vertex was queried with at least n-3 vertices, then I can get the isomorphism class of the tree, and therefore I can get the maximal distance, and also I can find a pair of vertices at maximal distance. So this is the lengthy part. That whenever I have a query graph which satisfies this, that every vertex is queried with at least n-3 others, then there is a vertex for which I know the distances to all the other guys. So there is lots of small steps, so it's case analysis, whatever. You have to believe me, or you have to look it up in the manuscript. And then, of course, if we have this vertex u, then again, as always, then we think about any possible consistent trees as rooted trees with u as a root. So it's neighbors, second neighbors, so at distance 2 and distance 3, and so on. And then what we do is that we define the property of being nice recursively. U is nice, because that's the root. And what we want is that the vertex is nice, so we are doing layer by layer, if its parent is nice, and in these, so what are we going to do? Well, we want to say that if this is the graph, I mean, if a query graph satisfies this property, then any two consistent trees, any pair of consistent trees is isomorphic. So we need to define an isomorphism between T0 and T1. And what we are going to do is that first we define the isomorphism between the nice vertices. That will be easy because they are the isomorphism, we'll just leave them where they were, and then trying to extend it. So how does this go? So nice meaning that, again, the root is nice, and then something is nice if its parent is nice, and also the set of its children is the same in the two trees. This is the definition. And then, of course, well, U has this property because we know the distances from U. That was the first bullet point, that U is a vertex for which we know all the distances. So that means that the set of its neighbors are just those that are at distance 1 from it. So it has this property. And yeah, so of course it's a subtree, because for being nice, that means that your parent is also nice. So it's a subtree. And then, sorry.
Niceness. So I understand U is nice, and then when the two children of U, when the child of U is nice again.
So the parent has to be nice. In the case of U, it's given. And then in T0 and T1, you look. So these.
What is T0 and T1?
So someone is giving me a query graph with the property that every vertex is queried with at least n-3 others. And now I'm looking at all the trees that are consistent with my answers. So let T0 and T1 be two such consistent trees, but I need to show that they are isomorphic, so I need to define an isomorphism from T0 to T1. And the way how I do it, that I define these nice vertices, my isomorphism.
You just fix two trees that are isomorphic, that are consistent with the answers.
Yes, and I need to show that they are isomorphic, because that means that I did indeed get the isomorphic class of the hidden tree. Okay. Because it would be true for any pair of trees. Okay. So this is my plan. So I define these nice vertices, and for nice vertices, of course, I can just leave them alone. I mean, so X is mapped to X, and and then I need to do the others. I mean, for the non-nice vertices. And so here's a claim that if so suppose that U was a nice vertex at layer L-1, and now I have a vertex V in the next layer, and if it has at least 3 descendants in one of the trees, then actually it must have the same set of descendants in the other tree. And why is that so? Well, so far you were lucky, because all the pictures were done by by one of the PhD students, but this one is evidently from me. Yeah. So what do I want to show? So now I have 3. So this is V here, and it has at least 3 descendants. So that means that there is a V prime, one of these descendants, that must have been queried with V, because everyone was queried with at least n-3. So V was queried with at least n-3. So that was 2 exceptions. So one of the descendants cannot be an exception. And of course, if V prime was asked with V, then we know that it's a descendant, because we know the layers. So if V is from layer 7 and V prime is from layer 9, then the answer should be 2. And that shows that it's a descendant, and that 2 should be consistent both in T0 and T1. So we know that V prime is a descendant of V in both things. Okay, now let's get another one. So let V double prime be another one, and suppose it is a descendant of something else on the same level as V. So say this W. What does that mean? Well, first, that means that V double prime wasn't queried with V, and it wasn't queried with W, because otherwise we would know that who is the parent on that level. But that means we are out of those guys that weren't queried with V double prime. So that means that V prime and V double prime were queried. And if we ask this pair, then of course we will know that whether their lowest common ancestor is below V, and therefore they are both descendants of V, or they are above V, and then they are different. So that will tell us. And so if that was queried, then we know that actually they are from the same descendant same ancestor on this level. So that shows that, okay, so all of every descendant has to be in both ones. Okay, so that means what? Yeah, this was just the proof. So here's the other picture I managed to make. So the black guys are the nice, as always, and so for the nice vertices, we have the isomorphism just by definition, and so we want to extend it. Because of the previous claim, what we know that if this is not a nice vertex, then it can have at most 2 descendants, because if it has 3, then because of the previous claim, everything is determined, the layers are determined, so then it should be nice. So that means there are 4 types of descendants, or I mean 4 types of children of a nice, 4 types of non-nice children of a nice vertex. The green ones that do not have further descendants, the red ones that have just 1 child, the yellow ones that have 2 children, and the blue ones that have a child and a grandchild. So all what we need to show that in T0 and T1, we have the same number of all the 4 types. And then, of course, we can just make a pairing in between them. And this one I won't show, but of course, so the hard part is to show that we have the same number of yellows. But once that's done, it's trivial from there, because that means that the blues is just the number of descendants on this level. And then once they are out of picture, then the red ones are just the number of descendants on this level, and then the remaining on 1 degree. So the hard part is to show that we have the same number of yellow children in both, which I won't do. Okay, so this is the upper bound for this problem. And finally, if you are still with me, then so if I want to determine the complete tree, then instead of the lower bound of the degree or n-3, now I have n-2, because here are the counterexamples. So if V is not queried with neither with U1 or U2, then I can answer in this way, consistent. I can answer in such a way that it's a star, and then V is either connected to U2 or U1, and all the distances are the same except these 2. So V is from distance 2 from the center and distance 3 from all the leaves, and other distances are completely the same. So this shows that, okay, this shows the lower bound, that in the query graph every degree is at least n-2. And then, of course, I need to show that if I remove a matching, a perfect matching or an almost perfect matching, then I'm still able to determine the tree. So how does that go? Well, I'm interested in the edges of the tree. I almost asked everyone, so that means I will get, luckily, lots of 1 answers, and those are edges. So what does it mean that, okay, how can I figure out that I didn't ask this pair, and yet it's an edge? Well, if U and V they form an edge, that means that for every other vertex, they are asked, because there is only 1 exception, so U and V are they're each other's exceptions. And then the distance is, the difference of the distances is exactly 1, for no matter W I'm taking. And also, there is a W for which this sum is 3, so therefore I know that the distance of U and V is at most 3, and because of parity reasons, it's either 1 or 3. And then, so suppose I mistake. So these are the 2 possible things: either U and V form an edge, or there is a path of length 3 in between them. So I have to be able to distinguish. So how do I do that? Well, U and V have to be leaves, because if, say, there is a vertex U joined here, then this property is not satisfied for its neighbor, because here the distance is going to be 1, and for here it's going to be 4. Okay. So they are leaves, and this one wasn't asked, so therefore UX and VY, they were asked. So now the question is that, of course, so if XY was asked and the answer is an edge, then of course I know that then UV cannot be an edge, because that would be a cycle. And if this is not an edge, then of course they form an edge. So therefore, the other option is that that I can't distinguish between these two cases, that x, u, v, y is a path, or u, x, y, v is a path. But now I can repeat my previous argument. So I concluded that u and v are, if I'm not able to tell which one is the situation, then u and v have to be leaves, so there is no edge leaving from there. But then I can repeat it and say the same for x and y. So there is no edge going out from x, u, v, and y. So that means if n is more than 4, then this confusion doesn't occur. So in that case, I can indeed, with removing a matching doesn't confuse me. Okay, I managed to sketch the proofs as all the statements I said. So thank you for your attention.